Hey class, this is Mr. Joseph, and since I'm going to be gone today, I'm recording this lesson as a video lecture. So let's go ahead and get started. You got today we're doing section 8.3 over matrix inverses. You should have these notes on your desk and ready to go. Okay, so let's go ahead and get started. Go through them. Before we talk about matrix inverses, I want to kind of give you an analogous situation that you might be more familiar with. The real number equation a times x equals b. If you were to solve this equation, you could do it by dividing both sides of the equation by a, or you could do it by multiplying by 1 over a, right? That's the same as dividing both sides of the equation by a. And since 1 over a times a is 1, you'd be left with x equals 1 over a times b. So you'd have solved it for x. And then just let me remind you that 1 over a is known as the reciprocal of a, or the multiplicative inverse of a. And I can write that as a to the negative 1. So an a with an exponent of negative 1 is equivalent to 1 over a. And because it's the multiplicative inverse, a to the negative 1 times a equals 1. Right? That's what makes them multiplicative inverses. Okay? So I could write this equation as a to the negative 1 times a times x equals a to the negative 1 times b. A to the negative 1 times a, like I said over there, is equal to 1. So that's 1 times x, or just x, equals a to the negative 1 times b. Okay? So we've solved that real number equation for x. Now we're going to do the same thing for matrix equations. So if I have a matrix equation, say matrix A times matrix X equals matrix B. To solve this for matrix X, if I want to know what does matrix X equal, I can't divide both sides by matrix A because division isn't defined for matrices. But what I can do is multiply both sides by the inverse of matrix A, just like I did. I multiply both sides of the equation here by the multiplicative inverse of the number a. Okay. And just like for the multiplicative inverse of a, just like a to the negative 1 times a equals 1, here we've got a inverse times a equals not 1, but the sort of matrix equivalent of 1, which is the identity matrix. An identity matrix, again, is any matrix that is a matrix that when you multiply it times another matrix, you can just get the original matrix back. Just like when the number 1, you multiply by any number, you just get the number back. Okay? And just a word about the notation. This negative 1, unlike that negative 1, doesn't represent an exponent. We're not raising the matrix to the negative first power. It's just sort of a notational thing that that's just how you write the inverse of the matrix. Okay. All right. And since A inverse times A equals the identity matrix, this becomes the identity matrix times X equals A inverse times B. And the identity matrix times any matrix is just that matrix, so we can answer our question here. Matrix X is the inverse of A times B. So we've solved that matrix equation. And that's what your notes are describing here in this little box. If matrix A is an n by n matrix, and that actually implies that the matrix has to be square, n by n, the same number of rows as columns. So the only square matrices will have inverses, and not even all square matrices will have inverses, as we'll see later. And if I is the identity matrix, for an n by n identity matrix, if there exists a matrix A inverse such that A times A inverse equals the identity matrix, or the inverse of A times A also equals identity matrix, then A inverse is called the inverse of A, and it's read as A inverse. Okay. Okay. Let's look at an example problem. The kind of most basic type of problem that we could look at is I could give you two matrices like I'm doing here and ask you if they're inverses or not. So that one's fairly simple. Since we know that a matrix and its inverse multiplied will equal the identity matrix, we can just simply test that. So if I have, let's see, if I have matrix X is -1, 2, -1, 1, and matrix Y is 1, -2, 1, -1, and I want to see if they're inverses, I can just find X times Y and see if it's the identity matrix, but I also want to find Y times X and make sure it's the identity matrix too, because we know, or we learned in 8.2 that matrix multiplication is actually not commutative. So just because X times Y equals identity wouldn't mean Y times X, and you can check both of these. So this is kind of a quick review of matrix multiplication. I'm going to do this sort of quickly since we went over this in 8.2. Remember, for matrix multiplication, I want to check the dimensions of each of the factors. So 2 by 2, 2 rows, 2 columns. This is also a 2 by 2. The inner dimensions match up, and so it's defined, and the outer dimensions give us the dimensions of the product, a 2 by 2. So 2 rows, and 2 columns. Okay. Now to get row 1, column 1, the entry in the product, I just do row 1 of the matrix X times column 1 of matrix Y. So -1 times 1 plus 2 times 1 is 1. And to get the entry in row 1, column 2, I multiply row 1 times column 2. So -1 times -2 plus 2 times -1, that's 0. For this entry, this is row 2, column 1. So I do row 2 times column 1. -1 times 1 plus 1 times 1, 0. And finally, row 2, column 2. We're going to do row 2 here times column 2 there. -1, -2 times -2 is 2, plus 1 times -1 is 1. So X times Y, we do get the identity matrix. And I'll leave Y times X as an exercise that you can do. You can kind of confirm, just for the sake of time, since it's a video lesson, I don't want to go too long, but for the sake of time, if you multiply Y times X, you should get the identity matrix. So you can write X is the inverse of Y, or Y is the inverse of X. They are inverses of each other. Okay? And again, I'll leave Y times X as an exercise that you can do.